By every modern rule, this tower should have collapsed centuries ago. It rises more than 200 feet above northern China. That is roughly the height of a modern 20-story building, but there is no steel skeleton inside it, no reinforced concrete core, no modern shock absorption system. Its main structure is wood, yet nearly 1,000 years later, it is still standing. And the strangest part is not what you can see. From the outside, the tower appears to have 5 stories. Inside, it has 9 structural levels. 4 of them are hidden between the floors visible from the ground. Those concealed levels may be one of the main reasons the tower survived. This is the Sakyamuni Pagoda of Fogong Temple, better known as the Yingxian Wooden Pagoda. It was built in the year 1056 in what is now Shanxi province. For centuries, it has endured wind, rain, earthquakes, repairs, and human conflict. From a distance, it looks almost weightless. Its roofs seem to float above one another, but standing at the base tells a different story. The eaves project far beyond the walls. Massive timber columns rise from a broad stone platform. Every floor carries another roof, another frame, and another enormous layer of weight. A wooden structure this tall should be vulnerable to almost everything. Wood dries, it shrinks, it cracks, connections loosen, columns lean, and the taller the structure becomes, the more dangerous every movement can be. So why did this tower not fail? The answer is not one perfect joint. It is an entire system designed so that thousands of imperfect parts can support one another. Start with the hidden floors. The 5 large roofs create the impression of a 5-story tower. But between those visible stories are 4 intermediate structural levels. They are not empty spaces. They contain additional beams, columns, floors, and braces. Instead of allowing one very tall section of timber to rise unsupported, these hidden levels divide the tower into smaller connected frames. They tie the columns together. They reduce the distance each column must stand without lateral support. And they create more places where forces can move from one part of the tower into another. In other words, the tower is far more layered inside than it appears outside. But the hidden floors are only the beginning. Cut horizontally through one level, and something even more unusual appears. The structure is organized around 2 rings of columns. An outer ring supports the walls, balconies, and projecting roofs. An inner ring surrounds the central space. Beams and bracket systems connect the 2 rings at every level. The result is almost like one wooden tower built inside another. The outer frame and inner frame do not work separately. They brace each other. They limit each other's movement, and they give the tower more than one path for carrying weight. If one connection weakens, nearby members can accept part of the load. If one frame begins to deform, the other can help restrain it. Engineers call this redundancy. It means local damage does not automatically become total collapse. The tower's octagonal shape adds another advantage. A long rectangular building usually has strong and weak directions, but an 8-sided tower distributes columns and beams around the center. Wind or ground motion can arrive from almost any direction. The load can then travel through several connected faces instead of one dominant front wall. That helps the building resist twisting and uneven movement. But this still leaves a major problem. The roofs are extremely heavy. Each one extends far beyond the supporting walls. Why does all that weight not crush the columns below? The answer can be seen beneath the eaves. Layer after layer of wooden blocks and projecting arms spread outward above every major column. These bracket clusters are called Dougong. They are beautiful, but beauty is not their main job. Dougong acts like structural machinery. Instead of forcing the roof load through one narrow point, each layer spreads across a wider area. The weight moves through overlapping wooden pieces, then into beams, then into columns, then downward toward the stone platform. Each bracket cluster creates many contact surfaces. Under normal gravity, those surfaces are pressed tightly together. That pressure helps the system remain stable. But gravity is the easy test. Now let the ground move. An earthquake begins beneath the stone platform. The base shifts first. The lowest columns begin to respond. Beams carry the motion into the inner and outer rings. Dougong clusters compress and rotate by tiny amounts. Upper floors begin moving a fraction of a moment after the lower floors. The tower sways, but it does not behave like one rigid block. Its movement is divided across many levels. Its joints do not all react at exactly the same time, and that difference matters. A perfectly rigid structure can attract enormous forces during an earthquake. If it cannot bend, rotate, or release that energy, it may crack suddenly. The wooden frame behaves differently. Its connections can move by very small amounts, while remaining joined. That is where mortise-and-tenon construction becomes essential. A projecting tenon fits into a matching mortise. Other pieces overlap, interlock, and clamp one another through shape, pressure, and gravity. These joints are strong, but they are not completely rigid. During vibration, they can rotate slightly, they can compress, they can slip by a fraction's inch. Wood surfaces press and rub against one another. A small amount of energy is lost through friction and local deformation. One joint cannot save a tower, but this building contains thousands of connections. Tiny movements, repeated across all those contact points, change the response of the entire structure. The tower survives not by refusing to move, but by controlling how it moves. Think of it as a giant wooden organism. The columns are the bones, the beams are the muscles, the Dougong clusters are the joints. The hidden floors act like belts holding the body together. When the ground shifts, different parts move by different amounts. The connections negotiate that movement. They spread it, they slow it, and they keep the pieces from separating. None of this was designed with computers. In 1056, every major timber member had to be shaped by hand. Columns were raised without modern cranes. Beams were lifted, aligned, and fitted using ropes, scaffolding, leverage, and human coordination. Each joint had to fit the members around it. A small mistake at one level could affect every level above. The builders were not simply stacking wood. They were assembling a three-dimensional structural machine. And they understood the material. They did not force wood to behave like stone. They allowed it to compress. They allowed it to bend. They allowed it to settle as the building aged. That flexibility did not remove danger. It gave the tower room to survive change. For centuries, winter air dried the timber. Summer humidity made it swell. Wind pushed against the broad roofs. Earthquakes tested the joints again and again. Repairs altered parts of the original system. And time slowly changed every connection. The tower standing today is not untouched. It is the result of continuous adjustment, but surviving the past does not guarantee surviving the future. Today, parts of the pagoda are visibly distorted. Some columns lean. Some structural layers no longer sit as evenly as they once did. Wood has cracked, shrunk, and weakened. Connections that once fitted tightly may now carry load in different ways. That creates a difficult problem for modern engineers. Making the tower stiffer might seem safer, but too much stiffness could force ancient wood to behave in a way it was never designed to behave. Replacing original members could erase historical evidence. Adding heavy reinforcement could save one area while increasing stress somewhere else. Intervene too little, and the deformation may continue. Intervene too much, and the tower may lose the flexibility that helped it survive. So modern preservation begins with observation. Engineers use laser scans, sensors, structural models, and long-term monitoring to understand how the tower is moving today. The goal is not to transform it into a modern building. The goal is to help an ancient system continue behaving as itself. That requires restraint. It requires patience. And it requires accepting that preservation does not mean freezing a building in time. The greatest lesson of the Yingxian Wooden Pagoda is not that wood can last forever. It can't not. The lesson is that durability does not always come from perfect rigidity. Sometimes durability comes from allowing movement without allowing separation. The builders did not force wood to behave like stone. They allowed it to compress, bend, slide, and settle. The Yingxian Wooden Pagoda is still standing, not because it never moved. It is still standing because its parts learned how to move together.